In this module, I'll look at how Platform Process Manager workflows are used within the Platform Application Center. I'll start by logging in. Once logged into the Application Center, I'll select the Jobs tab to access jobs and workflows. When Platform Process Manager is installed, the Platform Application Center becomes workflow aware. It can handle workflows and subflows just like any other Platform LSF job. In addition to being able to submit and manage jobs, I have full access to flow definitions. These can be my own definitions or definitions that I've been granted access to by other users. Some of the jobs running on the cluster are standard LSF jobs, as I see here. Other jobs are actually complete workflows, each comprised of multiple steps. I can recognize workflows because they're indicated by a flow identifier, the user ID that the flow is running under, and the flow name. When I select a regular LSF job, I see details about that job in the lower panel. I can view the job's output, suspend it, resume it, and so on. When I select a workflow, however, I see additional detail. I can view the flowchart, look at subflows and jobs, and view related data and flow history. I'll resize the lower panel to make more room. This is a sample computational fluid dynamics workflow. It runs by itself periodically to update model performance based on the latest design data in a central engineering database. Preferences that were configured using the Platform Process Manager Flow Editor are reflected here. I also see version-related information showing updates to the flow made over time. Let's look at the workflow itself. This flow is just for illustration, but is typical of what a real workflow might look like. The flow is dependent on input files that describe a structure's geometry, materials, and various simulation scenarios to be run. As I'll show in a minute, the information is generated automatically by a separate Platform Process Manager flow that builds these files based on periodic extracts from the central database. Once the extract is complete and all files are available, the workflow implements various steps like preparing input files for specific CAD tools. It also estimates runtimes for CFD simulations based on the size of the input decks. Based on the estimated runtime, the workflow then automates the decision process that decides where the flow is best run. Models that can run in just a few seconds are run locally. Medium-sized flows that take tens of minutes or hours to run are handled on a local compute cluster. For these types of jobs, it makes more sense to pre-process the data, segment the structure into components, and run models in parallel on the cluster to get a result more quickly. After the parallel threads run, results are aggregated and some post-processing occurs. Some jobs might strain our local capacity. For these jobs, it might make business sense to select another cluster connected via Platform Multi-Cluster, or perhaps use resources from an external cloud provider. Decisions like this depend on a number of factors like runtime estimates, how busy our local cluster is, whether needed datasets and licenses exist remotely, and the estimated time and cost involved in transferring large datasets. Platform Process Manager enables organizations to automate these kinds of decisions. If it makes sense to run the job remotely, I can start the process of transferring files. Otherwise, I can shunt the job back to an appropriate queue on my local cluster if the cost of running remotely is too high. In some scenarios, I might elect to do both at the same time, queue the jobs locally, but also start to transfer the data remotely as a contingency in case local resources prove too hard to come by. Once it's clear that one path will succeed, the other can automatically be made to terminate to save resources. I can automate these kinds of decisions that would otherwise require human judgment and intervention. For any workflow like this, whether running or complete, we can drill down and get details on workflow steps. I'll select the Subflows and Jobs tab. In this view, I see details about individual steps in the workflow. I see information including whether jobs are running, waiting to run, or completed. For those steps that ran as an LSF job, I see the job ID. I can click on this to get additional detail about where and how the job ran. This workflow involves 19 components. Workflows can be comprised of jobs, job arrays, local jobs, variable jobs, and even other entire workflows. I'll show an example of this in a moment. First, let's look at the different workflows that are available to us. I can look at flows either by state or by user. In this view, I'm looking at the various workflow definitions owned by the LSF administrator. I can see the name of the workflow, its state, and whether the workflow is published and thus available to other users. Various instances of these flows are shown in the lower panel. In this case, I have two flows that have been released and will run automatically. I mentioned that we periodically generate input files from the design database. The workflow that does this is called refresh from DB. This flow is triggered repeatedly but only on certain dates, defined in a custom calendar called resource DB data. Those familiar with Unix cron will recognize the syntax that triggers this flow. It runs twice each hour at 15 minutes and 45 minutes past the hour. This ensures that the data inputs to the CFD models are always current. The CFD flow that we just looked at can be safely triggered as soon as data is available. In this example, rather than waiting to trigger the flow manually, we use a Platform Process Manager feature called Proxy Events. Our CFD update flow thus runs automatically as soon as it detects that the other flow is complete. I can look at the workflow that extracts data from the database by clicking on it. Now the list below is filtered to show recently completed instances of the workflow. Another flow instance should kick off by itself shortly based on our calendar expression. I'll click the General Info tab. I see the description of the flow as before. The description tells us that this flow extracts data every 30 minutes. Flows can be triggered by various types of events or combinations of events. These include calendar expressions or the state of individual jobs or flows. In this case, the flow is triggered by the calendar expression we looked at earlier. I'll look at the workflow that produces the CFD input files. In this view, I see the logic of the workflow. An initial step determines what data is required, and based on this assessment, various jobs are triggered that extract data from different databases. In this completed flow, only an extract from the MySQL database was required because other data was found to be current. I mentioned earlier that it was possible to incorporate workflows inside other workflows. I'll show an example of this and run a workflow end-to-end for illustration. I'll select the first workflow called Demo Master Flow. This flow is not triggered by any events, so I'll trigger it manually. Flows can be triggered from the command line or from within scripts using the jtrigger command as well. After a moment, our flow is running. By state to see all the running flows. Now I'm looking at both running jobs and running flows. Flows can overlap in time or run in parallel working on different data models as we see here. There are several instances of our CFD flow running presently. Each of these results in potentially dozens of Platform LSF jobs, depending on the model and the decisions made in executing the flow. I'll expand the lower panel as before. And I'll look at the new flow I just triggered. This flow involves a pre-processing step and then two subflows that execute in parallel. From the color coding, I see the pre-processing step is complete and that the two subflows are running. I'll expand the first subflow and watch it progress. I can right-click on any element to expose options. I'll select Expand from the right-click menu. The first step in this workflow is just being scheduled. It will generate a random value, and depending on that value, a variable expression step will trigger one of three different scenarios. After a moment, the random inputs are computed, and the variable expression step selects scenario B. This job is now being scheduled to the cluster. While we wait for the subflow to complete, let's return to the parent flow. I'll select subflows and jobs like before. Between the main job and various subflows, there are a total of 15 elements associated with this flow. Notice that our scenario B on the first subflow has been scheduled and is now running. I can look at data associated with this flow and any of its component jobs if I choose. Because I can view and manipulate data through the portal anytime, I can assess the progress of workflows and workflow steps and easily share results with other users. I'll return to the flowchart view to see how the flow is progressing. The second subflow is complete now, but the first is still running. I can check runtime attributes to see how long this flow has been running. I can also do other things like view history, look at flow variables, or see dependencies between other jobs and flows. Here I see the attributes of the first subflow. This concludes our quick demonstration of Platform Process Manager. Thank you for your attention.